Welcome to our presentation. I am pleased to introduce myself, Yamuna, professor working in the Department of Chemistry at Amrita Vishwavidyapitham, Coimbatore campus. Our research focuses on many cutting-edge areas, including porphyrin functional-age carbon nanomaterials for nonlinear optics, and composite material for supercapacitor fabrication of composite material for supercapacitor application, and nanomaterial for medicinal and sensor applications. So recently we published an article in the prestigious RSC Applied Interfaces. So in this video we present highlight of those findings.
I am Anakha D, a PhD graduate in chemistry from Amrita Vishwavidyapitham, Coimbatore campus. My career highlights include publications of 14 peer-reviewed journal articles. My research interests are centered on nanomaterials, supercapacitors, medicinal applications, and material science. This video provides an information about the findings in our recent publication, High-efficiency CuO-CB6 cobalt aluminum LDH nanocomposite electrode for next generation energy storage. Coming to the introduction section, supercapacitors are known for their enhanced energy delivery capabilities and higher energy density compared to conventional capacitors. This has led to growing interest in layered double hydroxides. They are termed as LDHs, a type of anionic clay used to create advanced nano architectures that improve supercapacitor performance. Recently, researchers have developed a growing number of advanced and innovative nano architectures based on LDHs to improve the pseudo-capacitive performance. The synthesis of copper oxide nanoparticles stabilized cucurbit 6 uril, that is termed as CuO-CB6, was motivated by the abundance of copper and the compound's superior binding selectivity, making it a promising and readily available electrode material for energy storage. Next, coming to the methodology section, this scheme illustrates the synthetic pathway for the CuO-CB6 cobalt aluminum LDH nanocomposite, starting from the precursor CuO-CB6 and cobalt aluminum LDH components. 3 different nanocomposites of CuO-CB6 cobalt aluminum LDH were synthesized using wet impregnation method with ratios of 1:1, 1:2 and 2:1 for comparison and analysis. The precursor cobalt aluminum LDH was synthesized separately using the urea hydrolysis method. Next, coming to results and discussion, FTIR spectral analysis was used to study the structural characteristics of the synthesized materials. The spectrum for CuO-CB6 showed peaks corresponding to the CB6 capping agent and a metal-oxygen bond, confirming the formation of CB6 stabilized CuO nanoparticles. Cobalt aluminum LDH exhibited characteristic bands related to OH groups and interlayer water molecules as well as carbonate ions. The FTIR spectrum of this 1:2 nanocomposite showed shifted vibrational bands compared to the pristine components, which confirms its successful formation. Next, coming to XRD analysis. XRD analysis confirmed the successful synthesis and structural properties of the materials. The crystal phase of the CuO nanoparticles was identified using JCPDS and ICDD card numbers, and their monoclinic structure and average crystallite size of 14 nanometer were determined. The cobalt aluminum LDH diffractogram exhibited distinct peaks that were in close agreement with established JCPDS and ICDD card numbers. The XRD pattern of the 1:2 nanocomposite confirmed its formation by showing shifted diffraction peaks compared to the pristine CuO-CB6 and cobalt aluminum LDH, which suggests that CuO-CB6 nanoparticles are confined within the cobalt aluminum LDH structure. Next, coming to FESM EDX analysis. Here, the structural morphology and elemental composition of the materials, cobalt aluminum LDH and 1:2 nanocomposites were analyzed using this FESM EDX analysis. The cobalt aluminum LDH exhibited a smooth nanosheet surface morphology. The 1:2 nanocomposite was confirmed to be formed by the presence of spherical shaped CuO-CB6 nanoparticles situated between the layers of cobalt aluminum LDH nanosheets. Elemental mapping from the EDX analysis showed a uniform distribution of all the elements including copper, oxygen, cobalt, aluminum, nitrogen and carbon within the nanocomposite. Therefore, this analysis confirms the CuO-CB6 is successfully positioned within the cobalt aluminum LDH layers. Next, coming to the electrochemical performance of CuO-CB6, cobalt aluminum LDH and nanocomposite. So first is cyclic voltammetry. The electrochemical behavior of the synthesized materials was examined using cyclic voltammetry. The CV plots for cobalt aluminum LDH, CuO-CB6 and 1:2 nanocomposite are displayed distinct redox peaks in a 1 molar KOH electrolyte at varying scan rates from 10 to 80 millivolt per second within the voltage range of minus 0.5 volt to plus 1 volt. The CV plot of bare cobalt aluminum LDH reveals an anionic peak at approximately 0.57 volt, signifying the formation of cobalt 3 oxide, that is COOOH. Besides, a cathodic peak during the reverse scan at 0.24 volt, which is attributed to the reduction of cobalt 3 to cobalt 2. The CV plot of bare CuO-CB6 reveals a pair of redox peaks at approximately 0.85 and 0.218 volt, confirming the formation of copper 3 oxide and the reduction of copper 3 to copper 2. The clearly defined peaks confirm the remarkable electrochemical reversibility of the active materials. The CV plots for the different nanocomposites showed varying results. The 1:2 nanocomposite had a significantly larger CV curve area compared to the pristine cobalt aluminum LDH and CuO-CB6 at a scan rate of 80 millivolt per second, which is a result of the deposition of CuO-CB6 on the cobalt aluminum LDH sheet. Next, coming to Dunn's approach. So, Dunn's approach was used to plot V raised to 0.5 versus IV raised to minus 0.5 for 1:2 nanocomposite at potentials of 0.4 and 0.43 volt to identify the contributions from diffusion controlled current and capacitive current. The data also identified that as the scan rate increased, the diffusion controlled current for 1:2 nanocomposite also increased from 21% to 42%. Next, coming to galvanostatic charge discharge curve. So, GCD measurements were conducted to understand the pseudo-capacitance behavior of this nanocomposite. The GCD curves for cobalt aluminum LDH, CuO-CB6 and 1:2 nanocomposites were analyzed at varying current densities. The curves for all three materials exhibited a non-linear characteristic and the specific capacitances were determined from these measurements. The 1:2 nanocomposite demonstrated a longer discharge time and superior electron transport compared to its individual components. This is attributed to the improved ion transport of CuO-CB6, which is confined within the layers of cobalt aluminum LDH. The specific capacitance values were found to decrease as the current density increased. This is because electrolyte ions require more time to diffuse into the electrode's active surface region at higher current densities. The specific capacitance values of both pure cobalt aluminum LDH and CuO-CB6 are significantly lower than that of 1:2 nanocomposite. This suggests that the deposition of CuO-CB6 on the surface of cobalt aluminum LDH layer is crucial for improving the specific capacitance. The enhanced specific capacitance of 1:2 nanocomposites is attributed to its improved charge transport behavior and a greater number of active sites. Additionally, the nanocomposite demonstrated excellent long-term cycling stability, which retains 79% of its specific capacitance after 10,000 cycles at the current density of 7.27 ampere per gram. The specific capacitance value continued to decrease, reaching 1171 farad per gram at the 10,000 cycle. So, this drop is due to the abundance of new electroactive sites facilitating rapid electrochemical redox reactions, which then slows down. The 1:2 nanocomposite demonstrated enhanced Coulombic efficiency and retained 79% of its initial specific capacitance after 10,000 cycles. As a result, this remarkable stable 1:2 nanocomposite is suitable for use in long-term energy storage devices. Next, coming to electrochemical impedance spectroscopy. So, this EIS analysis was used to evaluate the resistance of ion diffusion in that nanocomposite 1:2 electrode material. The 1:2 nanocomposite had a lower RS, that is solution resistance value of 0.58 ohm compared to the pristine CuO-CB6 and cobalt aluminum LDH, which had values of 0.83 ohm and 0.78 ohm. This lower resistance value in 1:2 nanocomposites indicated its enhanced electrical conductivity when compared to the pristine material CuO-CB6 and cobalt aluminum LDH. Next, coming to Ragon plot. So, this Ragon plot was also used to show the relationship between energy density and power density for all the materials. At a current density of 0.45 ampere per gram, the nanocomposite achieved a higher energy density of 63.87 Wh kilogram raised to minus 1 and a power density of 114 W kilogram raised to minus 1. For comparison, at the same current density, pristine CuO-CB6 recorded an energy density of 36.30 Wh kilogram raised to minus 1 and cobalt aluminum LDH showed an energy density of 15.04 Wh kilogram raised to minus 1. These results confirm the superior performance of the newly synthesized 1:2 nanocomposite compared to similar materials reported in the literature. So, next I would like to conclude this talk that this study involves the incorporation of CB6 stabilized CO nanoparticles onto the cobalt aluminum LDH layers through wet impregnation method to produce 3 different nanocomposites. They are 1:1, 1:2 and 2:1 nanocomposite. The electrochemical performance of the synthesized nanocomposites were analyzed through cyclic voltammetry, galvanostatic charge discharge, and electrochemical impedance spectroscopic analysis. The 1:2 nanocomposite, it exhibited a specific capacitance of 1862 farad per gram at a current density of 0.45 ampere per gram as determined by GCD analysis. And the incorporation of CuO-CB6 onto cobalt aluminum LDH layer decreased the resistance, and it has improved the electrical conductivity through EIS analysis. Additionally, GCD data indicated that 1:2 nanocomposite exhibited a long-term cycling stability of 79% even after 10,000 cycles at a current density of 7.27 ampere per gram. Thus, the synthesized 1:2 nanocomposite can be served as a promising electrode material for supercapacitor performance. Thank you.